Hello. So in this lecture, I'm first of all going to talk about the binomial theorem, which we're going to prove using induction. And I'm then going to change tack slightly and start talking about sets. So the binomial theorem is probably something that you've come across before. It gives you a way of, as a kind of rule for expanding a bracket, like x plus y to the power of n. And we're going to prove that in a second, but before we get there, I want to just do a couple of things as a kind of preliminaries. So first of all, I'm going to define the binomial coefficients. So I'm going to say that n and k are natural numbers, and then I'm going to define the binomial coefficient as n choose k. So we write this as n kind of over k, but without a horizontal line, surrounded by brackets. It's also sometimes written nck, like that. And this is just defined in terms of some factorials. It's defined as n factorial over n minus k factorial, k factorial. And it works, this definition, for k in between 0 and n. And it's quite handy if we can define this so that it works actually even if k is bigger than n. So I'm going to also just define it as, this is not really very important, but I'm going to define n choose k to be 0 for k larger than n. Just so that this is given some kind of definition for every natural number n and k. So this is the number of ways of choosing k things from n things. And you probably may have come across it in probability, but it springs up in all sorts of areas of maths. It's maybe worth me just pointing out, in case you're not aware, that 0 factorial is 1. And we need that in order to make sense of this definition when k is 0 and when k is n. So these binomial coefficients are what appear in Pascal's triangle. So I'm just going to draw out a bit of Pascal's triangle. So these appear in Pascal's triangle, and we can draw Pascal's triangle by saying that each row of the triangle corresponds to a different value of n. So n is 0, 1, 2, 3, and so on. And then writing out each of the non-zero binomial coefficients. So for n is 0, the only one that's not 0 is for k is 0. So 0 choose 0, which is 1. For n is 1, there's 1 choose 0 and 1 choose 1. And both of those are 1. For n is 2, we have 2 choose 0, which is 1, 2 choose 1, which is 2, and 2 choose 2, which is 1. For n is 3, we have 1, 3, 3, 1. And you can keep going, and you may well construct Pascal's triangle not by following exactly this definition here, but by using the feature that you probably are familiar with, that in each row of the triangle, each entry is the sum of the two entries above it, and you can construct it that way. That's actually a reflection of an algebraic result in terms of these factorials, which is what I'm going to write down now because we're going to use it. So I'm going to call this result a lemma. You may have not come across the word lemma before. We use lemma to mean a result that's going to be useful for proving some later theorem or proposition. It's usually something that's not particularly interesting in itself. So you probably saw in the previous lecture I used the words theorem and proposition. They tend to get used kind of interchangeably for some quite important mathematical result that you usually then want to prove once you've stated it. Theorem tends to be something that's kind of more important. But yeah, lemma is something that's technically going to be useful in the future. And another word that you might see used is corollary. A corollary is a result that follows on from some theorem. Usually it's like some kind of extension or a consequence of the theorem. Okay, but this lemma, I'm going to say let n and k be natural numbers. I'm going to say that k is larger than or equal to 1, and n is also larger than or equal to k, just in order for what I write down to make sense. Then the statement is that n choose k minus 1 plus n choose k is the same as n plus 1 choose k. And so hopefully you can see that this is a statement of the fact that the two entries in Pascal's triangle sum up to give the entry that's on the next line. So I've not written this k minus 1 very well. Let me just rewrite that, k minus 1. Okay, this is really easy to prove. It's just a case of plugging in the definitions. So the left-hand side here, just by definition, is n factorial over n minus k minus 1 factorial. So that's n minus k plus 1 factorial k minus 1 factorial plus n factorial over n minus k factorial k factorial. And we could put those on a common denominator. Given the factorials, there's lots of stuff in common already on the bottom of those two things. So if I write this on a common denominator, then on the bottom I'm going to write n minus k plus 1 factorial and k factorial. And in order to get that on the bottom, the first term I needed to multiply it by k. So on the top I'm going to have n factorial. Actually, everything's multiplied by n factorial. So the first term had to be multiplied by k. And then in the second term, I had to multiply by n minus k plus 1. So I have plus n minus k plus 1. And the k's there obviously cancel. So in fact on the top there I've got n factorial times n plus 1. That's just n plus 1 factorial. So I can write this as n plus 1 factorial. And on the bottom I'm just going to rewrite the first term as n plus 1 minus k factorial, k factorial, because that now is exactly the definition of n plus 1 choose k. That's the right hand side. Okay, so that's just completely straightforward algebra. Okay, but we're going to use this result in our proof of the binomial theorem, which I will write out now. So this is a theorem, the binomial theorem. We're going to let x and y be real or complex numbers, and we're going to let n be a natural number. Then the theorem says that x plus y to the power n can be expressed as the sum from k goes from 0 up to n of n choose k, x to the k, y to the n minus k. Okay, so this tells us that if we want to expand a bracket like this, then the way we can do that is by looking at Pascal's triangle and just read off the coefficients in our expansion that's going across one of the rows, well, the row n of Pascal's triangle. So let's prove this. We're going to do it by induction. So we'll say we use induction on n. So first of all, we're going to prove it works for n equals 0. So for n is 0, or the left hand side is x plus y to the power of 0. Anything to the power of 0 is 1, so the left hand side is 1. And the right hand side, with n is 0, then the sum, well, the only term in the sum then is k is 0, and that term is 0 choose 0, x to the 0, y to the 0. Well, 0 choose 0 is 1. So, and x to the 0 and y to the 0 are also 1, so the whole thing is just 1. Okay, so it works. Right, 1 equals 1. So we have it's true for n equals 0. Now we're going to suppose it's true for n, and we're going to consider whether it's true then for n plus 1. So x plus y, probably going to run out of space here because I've got to now write out quite a lot of algebra. So x plus y to the n plus 1, we're going to try and make use of the fact that we're assuming it's true for n. So we're obviously going to try and write this as x plus y times x plus y to the n, and then use the fact that we're assuming it works for n. So this is going to be x plus y times the sum from k is 0 up to n of n choose k, x to the k, y to the n minus k. Okay, so that was the inductive hypothesis that we just used. Okay, then the rest of the proof is actually just going to be manipulating the algebra of this term here. We had to play around with the sums a bit. This is something that you need to get used to, is being good at using indices in these kinds of sums. So I'm going to write this, well, first of all I'm going to expand out the brackets. So this is going to be the sum k is 0 to n of n choose k, x to the k plus 1, y to the n minus k, plus the sum k is 0 to n, n choose k of x to the k, y to the n plus 1 minus k. And then what I'm going to do, I'm going to move on to the next slide, is to take out the final term k equals n from this sum, and I'm going to take out the first term k equals 0 from this sum. It's just going to be convenient to do that in order to work with the algebra. So this is continued. This is going to be x to the n plus 1, that's the final term from the first sum. We're then going to be left with the, oops, that should say plus. We're going to be left with going from k is 0 up to n minus 1 now, of n choose k, x to the k plus 1, y to the n minus k. Then we're going to have, I'm going to take out the first term of this second sum, so this is now going to go from k equals 1 up to n, of n choose k, x to the k, y to the n plus 1 minus k, and then that first term that I pulled out is y to the n plus 1. And then you need to realize that the k that's in these sums is just like a dummy index. We could call it something completely different. It's only sitting there inside the sum. It doesn't matter if we write it as something else. And so I'm going to change the index in one of these sums so that it kind of looks the same as the index in the other one. And so what I'm actually going to do, I find this sometimes quite helpful. I'm just, in the first sum, I'm just going to change k. I'm going to call it something else. So it's easier to call it k hat. I'm just going to add a hat on top of all the k's. That hasn't done anything. It's just relabeled it. And then I'm going to say, let's call k hat actually k minus 1. If I do that, then I can rewrite this sum as something that goes from k is 1 up to k is n, and then it will look the same as in the second sum. So I'm going to write that out. So I'm only going to need one sum then. So this is going to go k is 1 up to n. And so the first sum is going to become n choose k minus 1. And then the x to the k hat plus 1, well k hat plus 1 is just k, so that's x to the k. And then we have y to the n minus k hat, that's n plus 1 minus k. And you'll see that these powers of x are actually the same as what we have in the second sum now. So then we have plus n choose k, x to the k, y to the n plus 1 minus k. The sum is around all of those, so maybe I should add an extra bracket to clarify that. And then we have that final term, y to the n plus 1. And now, so in this bracket, I could obviously factorize the powers of x. I have n choose k minus 1 plus n choose k, and that's what I just said in the lemma was equal to something else. So now we use the lemma. This is going to be x to the n plus 1 plus the sum k is 1 up to n of n plus 1 choose k, x to the k, y to the n plus 1 minus k. Then we have plus y to the n plus 1, and I'll just write here using the lemma. Okay, and then I notice that actually this sum could be expanded to include this x to the n plus 1 and the y to the n plus 1 if I just change this sum so it goes from k is 0 up to n plus 1, then those terms fit with the pattern. So that's just rewriting it. So I can write this as the sum k goes from 0 up to n plus 1 of n plus 1 choose k, x to the k, y to the n plus 1 minus k. And that is the right hand side, which is what we were trying to show. So that shows that the expression works for n plus 1. So then I need to write a concluding statement here. I'm going to say by induction the result holds for all n in the natural numbers. And that's the end of the proof. Okay, so if you've seen this kind of manipulation before, then I probably went through that maybe a bit slowly. If you haven't seen it kind of before, then this kind of fiddling with the indices, relabeling them, and shifting the index so that you can combine sums in a certain way is something that you'll probably see quite a lot of. Okay, so I'm going to take a pause there because I'm now going to change and start talking about sets more generally, not just the natural numbers. Okay, so I'm now going to talk a bit about sets. When I said that on the previous video, the auto-generated captions that we have on this software, I thought I was going to talk about something else. Hopefully this will be even more exciting. But I should say the captions, I'm going to try to correct them. It doesn't do a good job at understanding maths. And sometimes it produces nonsense, but sometimes it tries to make sense of what you've said, but gets completely the wrong end of the stick. So I will try to correct them, but if anything gets through, then please don't be offended by anything that the captions say. So we want to think of a set as a collection of objects. And we have already seen the example of the natural numbers. The objects are called the elements, or sometimes members of the set. Okay, and we write the set with elements A1, A2 up to AN, say, as curly brackets, A1, A2 up to AN. This would be a set with n objects in it. The order in which you write the things inside the curly brackets, it doesn't matter. It's the same set. Now, this definition is actually not very good. And we're going to see lots of examples that should make clear what we mean. But I'm also going to show you an example at the end of the lecture where this doesn't work. And the problem is that this phrase here, a collection of objects, is not very precise. It's not really clear what exactly that means. And if we interpret it in the wrong way, then sort of too broadly, then we might run into trouble. But it turns out it's not that straightforward to give a better definition of a set. And it's something that you'll have to wait until, I think, in the third year, a course on set theory to look into that more. So for our purposes, this is going to be okay, but we just need to be a bit careful about the fact that the definition is a bit loose. Okay, but I do want to define a subset. So here is a definition. So A is a subset of another set S if, and this should be fairly straightforward, if every element of A is an element of S. Okay, and we write that as A is a subset of S. This symbol means is a subset. Sometimes that would be read as A is contained in S. That would sort of mean the same thing. So with this definition, if A equals S, then that is a subset. So S is a subset of itself, but it's not a very interesting one. So if A is not equal to S, then it is called a proper subset. Okay. Now, one particularly important set that I want to give a definition of is the empty set. And that is just the set that actually doesn't have any elements in it. This is written as a 0 with a line through it. So this is the set with no elements. But that counts as a set. Okay, so we've seen the example of the natural numbers. Let me give you a few more examples of some sets. One of them, let me first of all take a subset of the natural numbers. Let's take the even numbers. So we could write that as the set of n in the natural numbers such that n is divisible by 2. So we saw this notation before. If I write a colon and then write some statement, it means it's the set of natural numbers n such that n is divisible by 2. And that is a subset of the set of natural numbers. Okay. We also have the set of integers. That's denoted by a z. So that includes negative ones. So that we could write as 0, plus and minus 1, plus and minus 2, and so on. Okay. We have a set of rational numbers. That's denoted by a q. So that is the set of numbers that can be written as a ratio of integers. So I can write that as the set of m over n such that m and n are integers. I should say z, otherwise I can't get negative numbers. And I just need to be careful that I don't divide by 0 there. So let me say n is greater than 0. So that's the set of rational numbers. These letters, by the way, with extra lines in them, this is called Blackboard bold font, and this is standard notation for these sets. You might see when you look in the typed lecture notes, some of them look a bit more fancy, but you don't need to make them look exactly like they look when they're typed. You just need to stick an extra line in them, and that'll do the trick. So we also have the set of real numbers. That's something that you're going to talk a lot about in the analysis course, so I won't say anything more about that. You also have the set of complex numbers, and you have an introductory course for those as well. But we could write those as the set of A plus IB, where A and B are real numbers. Okay, and where I is the square root of -1, whatever that means. Okay, all of these sets are sets of numbers. I'll just point out that none of them include infinity. Infinity is not a number. There are ways that you can extend some of these sets, and you will see at some point, you'll see the extended real line or the extended complex plane. That the sets have then been expanded to include some notion of infinity. But these sets themselves don't include infinity. Sets don't have to be sets of numbers, they can be sets of other things. In linear algebra, you will deal with sets of matrices. So we could have Mn of R. That is the set of m by n matrices with real coefficients. And you can have other variants like that. There's no reason that the sets need to be particularly mathematical objects, though. You could have a set of people, or a set of words, or a set of shapes. I quite like the set of emojis, which I tend to use quite a lot. But you can have all sorts of sets. Some other important ones that I want to tell you about are intervals, which are subsets of the real numbers. Or quite often it's helpful to think of the real numbers as the real line. So let me define those. If A and B are real numbers, with A less than or equal to B, then we can define an interval AB, so we write brackets AB, that is defined to be the set of X in the real numbers such that X is strictly in between A and B. If you write the same thing but with square brackets, so AB like that, then that means the same thing, but it includes the endpoints. So that's X in the real numbers, such that X is in between A and B, but could be equal to A or B. So an interval like this is called a closed interval, and an interval like this that doesn't include the endpoints is called an open interval. And you can mix and match, so you could have it open on one end and closed on the other end, and you just use a mixture of brackets then. Both of those are bounded intervals. We can also have unbounded intervals. So we write A infinity, even though infinity is not a real number, this is the notation that we use. That means the set of X in the real numbers such that X is larger than A, but with no upper bound. Or we could have, for instance, minus infinity to B, let's make it closed this time, that would be the set of X in the real numbers such that X is less than or equal to B. Okay, so those are intervals, and you'll see lots of those in analysis especially. The elements of a set could themselves be sets, and an important example of that is something called the power set. So let me give you a definition of that. So the definition is that the power set of a set A, which is denoted with a curly P of A, is the set of all subsets of A. Okay, so just think about that for a second. Let's give an example, see what that means. So let's suppose A is the set containing 0 and 1. In that case, the power set of A, so this is going to be a set containing subsets. So what are the subsets of A in this case? Well, one of them is the empty set. The empty set is a subset of all sets. We could also take a subset if we just take the 0 element, or if we just take the 1 element. So we could have a subset which just contains 0, or we could have a subset which just contains 1. Or we could have A itself, so we could have the set containing 0 and 1, which is A itself. And those are all of the subsets of A in that case. You might notice there's an instance of the binomial coefficient showing up here. There was one subset that contained no elements. There were two subsets that contain 2 elements, and there was one subset that contains 2 elements. This was like n choose k. I'll also just point out here actually that this thing here, curly bracket 0, is very different from just 0. This is a set containing 1 element, 0, and that's different. So this is something that people often confuse. I'll say, note that A is not the same thing as curly brackets A. Right, this is an element. This is a set containing a single element. And so even if the element is itself a set, if this A was the empty set, then this would not contain any elements, whereas curly brackets A, in that case, is a set that contains 1 element. That element is the empty set, but they're definitely not the same thing. Okay, so that's the power set. The next thing I want to do is to talk about how we can combine sets. So I'll say we can combine 2 elements, which I'll call A and B, as an ordered pair, which we write A, B. So the point about an ordered pair is that the order matters. So this is not the same as saying the set containing A and B. We could have combined A and B into a set that would have been written like with curly brackets. But if we write it like this, it means it's an ordered pair. And this is an example of where we have duplicate notation, meaning completely different things. So on the previous slide, I defined A, B like this as meaning an interval, an open interval on the real line. Now this is something completely different, but we're just using the same notation, and we have to understand from the context what the different notation might mean. Okay, you're probably familiar with this kind of thing as a vector. So if A and B are real numbers, then this is just a 2-dimensional vector. So I'll just point that out. If A and B are real numbers, this is just a vector. But the definition of an ordered pair is more general because the A and B don't need to be real numbers. They could be elements of some other set. Okay, but this leads me on to the definition of something called the Cartesian product. So I'm going to say, given sets A and B, the Cartesian product which we denote A cross B is the set of all ordered pairs A, B, where A is from the set A and B is from the set B. Okay. If B is the same set as A, then we write A crossed A as A2. We tend to pronounce that A2 rather than A squared in this context. So for example, this is an important one that you'll see in geometry. If A is the set of real numbers, then the Cartesian product is R2, which is the set of points on a plane. And you can describe the position of those points with a vector, which is the ordered pair in that case. And more generally, you can combine more than two sets like this. So I will say, more generally, if we had n sets, say, let's call them A1, A2, up to AN. So A1 crossed A2 up to AN would be the set of all ordered, well, they're not going to be pairs anymore, but they're called an n-tuple when there's n elements. So an ordered n-tuple, so that's going to be A1, A2 up to AN. Okay, and if the AI are all the same, we write this as AN. And you'll see that quite a lot, especially in geometry. You'll be dealing with R3, for instance, which is three-dimensional space. Okay, so that's Cartesian products. I want to close with a warning, and this is about the vagueness of our definition of a set. So this is going to be Russell's paradox. And so Bertrand Russell was one of the mathematicians who was helped kind of pioneer the development of set theory around about 100 years ago. So we're going to suppose that we try to define the following set. I'm going to call it H. It's going to be the set containing sets which have the property that they are not members of themselves. Okay, so this appears to be a collection of objects. The objects are sets, and they have to have the property that they are not members of themselves. Okay, and all of the sets that I've mentioned so far would seem to be in this set, because none of them are members of themselves. So for instance, the set of natural numbers, the elements are numbers. None of those elements is itself the set of natural numbers. And the same, we have the same issue with all of the sets that we've seen. So this set would seem to be quite large. It contains lots of sets. But the problem is whether H is itself in H. Because if H is in itself, then by the definition of what that means, it means H is not in itself. So that seems to be a contradiction. But if H is not in itself, then it exactly satisfies the definition that means it should be in itself. So this is the paradox. It doesn't seem to make any sense. Let me just try to write that down. So I'll say if H is in H, then by the definition of H, H is not in H. So that's a contradiction. On the other hand, if H is not in H, then it satisfies the condition such that it is in H. So H doesn't seem to be either in itself or not in itself. And so that's also a contradiction. Okay, and so the problem here is that this H that we've tried to define here really shouldn't be a set. And so this would be too loose a definition of what a collection of objects might mean. Okay, and with a more modern definition of a set, based on some axioms, then we wouldn't classify this H as being a set, and therefore trying to decide whether it's in itself or not just doesn't make any sense because it isn't a set. Okay, so this is not something that you should worry about too much. It's something that's quite interesting, and if you are interested in that, then you might have to wait in suspense until a bit later in your degree. For our purposes for the moment, we can work with the more naive definition, but we just need to be aware that there are some issues down the line. Okay, so let me just try to summarize what we've done there. So we've talked a bit about what a set is, and we've seen various examples of sets. We've seen an example of intervals on the real line. We've defined the power set, and we've talked a bit about the notation. We've also seen how we can combine sets as a Cartesian product, and then we've had a bit of a warning about the fact that our definition is not perfect.